Morning, everyone. Good afternoon, good evening, wherever you're connecting from. I'm Ira Feldman. I'm the Executive Director of MEPTEC, and I would like to welcome you to today's MEPTEC IMAPS Semiconductor Industry Speakers Series presentation. Thank you for joining us. And next in our speaker series, December 9th, Sandeep Razdan from Cisco will talk about the challenges and opportunities in silicon photonics packaging for network applications. Please plan to join us live for that event because we may not be able to post the slides or the recording. So please be certain to join us on December 9th. And then on December 16th, we're going to put together a slightly different event, which will be an informal holiday hangout. We'll have registration links for both these available next week. So please plan to join us on December 9th and December 16th at 11:30 a.m. We are working on the program for next year. If you're interested in speaking, please contact myself or David Town. In terms of future events, the next MEPTEC event will be on February 9th and 10th. The title is Too Hot to Test, talking about the thermal management of ICs during test, especially the large ICs for artificial intelligence and other advanced computing have significantly large thermal challenges. We are soliciting abstracts, so if you're interested in presenting, please send us an abstract by December 18th. Additional information is on the website meptec.org, or you may contact me. So look forward to that event. In terms of MEPTEC, MEPTEC is a membership supported organization. So if you haven't renewed or you're interested in joining us, please see our website or contact Betty Cooper, bcooper@meptec.org. We also have the availability of corporate sponsorship. So if your company would like to sponsor, we'd be more than happy to have you join us in support of MEPTEC. So today's Semiconductor Industry Speaker Series is Dave Kehlet from Intel. He's going to talk about chiplet technology for an emerging ecosystem. Dave is a researcher at Intel who's working on pathfinding, which is an Intel term for looking at next generation and future FPGA technology, including high-speed interfaces. And currently he is looking at the chiplet technology and those interfaces to help develop a new ecosystem for developing electronic systems. Dave earned a BS and MS degrees in electrical engineering from Stanford and holds 18 US patents in graphics and video. So I would like to welcome Dave.
Hello everyone, this is Dave Kehlet. It's great to join MEPTEC on this Thanksgiving Eve. And I want to talk about a topic that has really engaged me for the last 6-7 years, and that's chiplet technologies. I'll let you read the Intel legal disclaimer at your leisure. The first thing I'm going to discuss is really how did we get here, in a section I call Chiplets on the Rise. Then I'm going to talk about the state-of-the-art heterogeneous integrated packaging SHIP project. This is one that Intel won from the US Navy, and how we're using this to develop second-generation chiplet concepts, and then I will wrap it up.
So Dave, before you go further, let me remind the audience that we're going to be doing questions interactively. So if you use the Q&A tool and you pose questions, I will ask Dave at an appropriate time in his presentation. So,
sure, thanks, Ira. So the first section I call Chiplets on the Rise. It's the early days leading to the mother of invention. And folks who can think back to 2013 might remember this announcement that came from Altera, that Altera would switch from TSMC and use Intel on its 14 nanometer process. And once we dug into the Intel process and started working on it a bit, we discovered, it's a digitally focused PDK for very high performance processors. And to get our high-speed SerDes onto this process was going to take a little bit of time. So we thought of an alternative that leveraged Intel's EMIB technology for multi-die packaging. And you can see the press release came out a year later that we announced we would collaborate with Intel to use EMIB on multi-die devices. So you can see kind of the evolution here of how we came to use chiplets, because it was a way to solve a problem of how do you get the very high performance digital and our high performance analog into the same package. Now, to get some perspective on this, you can take a look back to the previous generation of component. This is Intel's Aria 10. And it had we call these transceiver columns on both sides of the die. And between the columns and the core fabric are thousands of wires. And these wires are transmitting data, clocks, configuration, and control. And now we were tasked with how do we disaggregate this monolithic design when it has thousands of wires. You can see that the traditional standard packaging technology just kind of gut feel wasn't going to be quite up to the task here. And this is where the high density packaging, in our case, Intel EMIB, but there are other technologies for silicon interposer, TSMC CoWoS, RDL packaging technologies. And what we get out of that is a 7 to 8 increase, 7 to 8x increase in IO density. You go from this 28 to 34 IOs per millimeter per layer to the high density, which gets us 250 or more IOs per millimeter per layer. So this was what allowed us to do that disaggregation and put the thousands of wires onto the new technology, the high density packaging technology, and deliver something that appeared to the user as a monolithic device.
So Dave, when you would talk about IO per millimeter, that's the beachfront distance or around the periphery of the die or the chiplet?
Yes, yeah, so the shoreline density that could be carried across between these dies in a 2.5D fashion. You can see kind of the red highlights on both sides here show the signals going across from die to die.
Thank you.
So kind of the takeaways from these early days, this advanced packaging technology really allowed some new thinking about microarchitecture, that you could perform die disaggregation. We ourselves did heterogeneous integration with Intel 14 and TSMC 20. Because this advanced packaging technology gave us high bandwidth and low latency that was near monolithic performance. And so we could transition from our previous monolithic design into a heterogeneously integrated design. So the next step on the early days here is the involvement of DARPA in a program called DARPA CHIPS. And it was this acronym for Common Heterogeneous Integration IP Reuse Strategies. It was a project that Intel won a large chunk of the research dollars on. The US government had this challenge, which was they were finding it was economically challenging for their defense contractors to build monolithic designs for each new generation of DoD system. So the DARPA organization created this program here. And you can see the quote from the ERI director, Bill Chappell, that they were working with Intel on integration strategies so you can do a composable design. And the idea was that you could take chiplets, these pieces of silicon, and put them together. And the purpose of CHIPS was to help come up with design tools and standards for aiding the development of heterogeneous integrated designs. Now, an outcome of the combination of Intel and Altera's own commercial development and the DARPA CHIPS involvement was this a portfolio of chiplets that I'm showing here. You can see, there's 10 or so chiplets that are already powered up or in production, and another dozen or so that are in development here. Out of the DARPA CHIPS effort came an interface PHY standard known as Advanced Interface Bus, AIB. And it was adopted by the DARPA CHIPS performers, including Intel, and is now a standard out of the CHIPS Alliance organization. I'll talk about that in a minute. And it's what I would call a de facto standard, just given the weight of the portfolio here of all these devices that are in silicon. You know, in the industry, it's still a competitive marketplace. So there are multiple ideas of how to do die-to-die here. But I would claim that the AIB has become a de facto standard just simply by the weight of devices being built by Intel, devices being built by other commercial organizations, as well as research universities. And so this takes us all the way from our Altera, Intel, DARPA roots, and as we'll see coming up, it's a central technology of the Navy's SHIP project that Intel was awarded in October. So the takeaway from this phase of chiplet evolution was the government stepped in. Industry couldn't really come up with a standard on its own. And this chiplet architecture, you can see on the previous page, one of those chiplets was what Intel calls the E-tile. And it was really a midlife kicker we were able to add onto Stratix 10 a year after Stratix 10 was in production, that gave us 56 gigabits per second capability and allowed a midlife kicker in a device way in advance of when the next generation, you know, in Intel's case, it's the Agilix 10 nanometer device. The architecture allowed us to give this midlife kicker without having to wait for the next generation main die. So at this point, I'm going to talk about the state-of-the-art heterogeneous integrated packaging project, the SHIP project, and how we are able to develop our second generation chiplet concepts within the SHIP project. So just kind of a recap of what did we accomplish in this first generation, if I can call it that, for these first 6-7 years of chiplet development. There's the famous quote from Gordon Moore here that a lot of people have quoted, that it may prove to be more economical to build large systems out of smaller functions which are separately packaged and interconnected. And this is his vision from 1965 that we are still realizing today. So I think it's fair to say that chiplets are extending Moore's law, that chiplets are commercially viable from multiple silicon suppliers. People like IR Labs, Jarrett Technologies, as well as defense industrial-based contractors. And what's enabled us to develop this portfolio of chiplets is an emerging ecosystem of IP, of standard interfaces such as AIB that's allowed us to get there. So now with the second generation of chiplets, while we've been doing this first generation, the bandwidth requirements of things like wireless and optical networking has really dramatically increased. So we want to evolve and have evolved the AIB standard to a 2.0 to handle this, and I'll talk some more about that in detail. We want to flow down some concepts that are familiar to system-on-chip developers and users, things like security, down to chiplet scale, which is a little bit more of a challenge now because you're dealing with something that is maybe 32 square millimeters, 64 square millimeters, and you don't have a an immense 600 square millimeter main die like you could on a very large SoC. Plus, we want to develop a more complete framework of enablement for chiplet developers. Developing any piece of silicon is a lot of work. Chiplets are no different. They're ASICs, and ways we can help developers with enablement and IP is definitely going to improve the ecosystem. So a little bit about the SHIP project. This is the announcement that came out of Intel beginning of October, that the Department of Defense awarded it to Intel to enable the US government to access Intel's state-of-the-art semiconductor packaging capabilities. So I got a photograph of an Intel factory out in Chandler, Arizona. And the bulk of the SHIP project is about packaging and manufacturing. but it's also about chiplet interface standards, protocols, and security. The government approached us and said, could you propose advancement in these areas of chiplet interfaces, standards, protocols, and security? And we did, and were awarded a substantial amount to go pursue the pathfinding here and realize this in standards and IP. With chiplet design technologies, I consider this as ecosystem development. We want to enable partners to develop chiplets, so things like chiplet interface standards, protocols, and security. And we need to do all of this on chiplet scale. We can't afford to use a whole lot of cost of silicon area to do this. And we get to build on our chiplet ecosystem experience, our heterogeneous integration experience. And experience is a really interesting thing. I think folks on the phone here will kind of get this, that if you have a lot of experience, it seems to be something extremely valuable. If you don't have a lot of experience, a lot of people think, well, experience doesn't mean a whole lot. Or even worse, could hold you back from new ways of thinking. But I think we might all agree that experience helps you move faster. And that's clearly how I see we're going to proceed on these chiplet design technologies. Now, I mentioned that these new applications need more bandwidth than our 1.0 technology provides. So if you look at the gigabits per second for an interface on Stratix 10, you can see it's about 2 terabits per second. And I just pulled out a couple public examples here. You can see the reference down at the bottom of the pages from Chariot Technologies, that their ADC DAC device is capable of generating 5 terabits per second. The IR Labs optical networking, Terrify, similarly capable of generating 5 terabits per second. And so this is more than the 1.0 technology is capable of handling. So it was time to scale up AIB to an AIB 2.0. And so we are developing a 2.0 interface to meet the demands of these high performance applications. And you can see a couple photos here. This is IR Labs integrated photonics module. So it has kind of a double challenge of packaging technology, not just for die-to-die communications, but also for package mounted photonics. And the Chariot radio ADC DAC here with its very high sampling rate that it wants to send it across over a 2.5D interface to FPGA based or ASIC based radio. So we've developed a draft specification for the Advanced Interface Bus 2.0. We have our externally facing standards are public. You can see the GitHub Chips Alliance site. And this standard here helps us continue to support this, what I consider an unmatched portfolio of chiplets. Now, a little bit about the Chips Alliance. It's the standard setting home of the AIB specification. The mission of the Chips Alliance aligns well with the AIB standard and AIB hardware open source. We have open source for AIB 1.0 in its own repository on GitHub under the Chips Alliance area. And you can see the members, a lot of top tier organizations are part of Chips Alliance, and headed up by a super sharp individual. Dr. Zvonimir Bandek is the chairperson of Chips Alliance, and it's a really interesting organization. The concept of hardware open source is still itself an interesting concept that our customer in the government, both DARPA and US Navy, they like the open source concept a lot because it ensures access to not just their IP in general, but also to things that they fund. It's out there visible and everybody can look at it, and it's a way of holding people like me accountable.
So a question on the open source nature, I mean, does that put the US at a disadvantage militarily? I mean, other entities could just use the same technology. I mean, usually having more people in an ecosystem is good, but how does the government view the the downside risk of that?
Well, yeah, this is not export controlled technology. There are alternatives, such as Lippincon from TSMC that are available internationally. I think they view this as it enables their contractors who may not have the economic heft to convince, you know, huge companies like Intel, TSMC, Global Foundries to do things. It helps their contractors access this technology, and I think that's where they see the real value in it.
Good. And before you get into 2.0, you talked about the speed as being one of the challenges that was solved in 2.0. Were there other challenges that you saw in 1.0 that 2.0 addresses?
Yes, yes, and so that's a great lead into this outline, and this came from Intel's Architecture Day. One of the Intel technology leaders, Ramuni Nagasetti, presented this slide, and you can see there's several vectors of performance improvement going on here. The first one is simply the bandwidth per wire. Now, this is a really interesting one because Intel at the same Architecture Day announced 224 gigabit per second SerDes. So going from 2 gig to 6.4 gig is not that big of a deal compared to something that's 2 orders of magnitude faster. However, you have to think about what's behind this technology, and can you implement this on a diverse set of silicon processes? We have AIB implemented on GlobalFoundries 40, all the way down to TSMC 7, Intel 10, Intel 14. So the bandwidth per individual wire one is a trade-off between the amount of silicon area that you want to spend on it and the accessibility of this technology and the applicability to really a heterogeneous integrated environment. Now, some of the other vectors that we're pushing, the bump density, this goes directly, the circuit today, I'll show you this, the circuit today is smaller than the bump array. So improvement in bump density almost goes directly to a cost savings on your device if we can have a smaller array. So you can see kind of the resulting metric that we like to use, bandwidth per millimeter shoreline, goes up dramatically with 2.0. And at the same time, now that we're pushing, 5 terabits per second up to 7 terabits per second, your energy per bit becomes very significant. So we're doing a low voltage IO interface to get the energy per bit down. And this is in my view, it's an engineering conservative estimate of energy per bit. The great thing about energy per bit is it's kind of hard to independently verify. And so there's a lot of claims out there. Now, as a 2.0, we have to maintain backward compatibility with our portfolio that represents really billions of dollars of semiconductor investment. So we'll continue that. So with this, we get something that is dramatically faster, up to 7 terabits per second, using a nominal 4 gigabits per second per wire, per interface that's maybe 8 millimeters of shoreline on the die. So this is really a path that we can serve those very high performance applications such as the optical networking and the RF direct sampling. Okay, so this probably really interests folks with packaging here. You can see as we're pushing this vector of the pitch of the micro bumps. With 1.0, we supported the 55 micron, 2.0. And if you look at the spec, the microbump pitch is not really a 1.0 versus 2.0 thing. It's just associated in time with 1.0 versus 2.0. We've come up with a really nice way of doing the microbump spacing such that you can easily gasket between bump sizes using straight lines, so that if you work this out on how you would connect these things up with only a half a bump jog, you can connect up between the 55 and the all the way down to 36 micron spacing. So now here's another look at it. And this is where I was going to the microbump pitch, saving you die area. So you can see on the upper right, this is the depth into the core that each one of these AIB microbump arrays pushes you. We kind of keep the shoreline constant. It's about 8 millimeters for a 24 channel interface. And you can do half size, quarter size interfaces as well. So the variable that the chiplet builder gets to really affect is the depth into the core with the different size of the bump array. Now, another way of looking at it on the left side, you can see you've got this micro bump array. This is a cross-section view. And then down underneath it, you actually have your IO buffers, your IO circuits, the sampling flip-flops. And right now we are micro bump array limited. And so the question is, you have this other area that's under the micro bump array. Can you use this for some other purpose? And in some cases, you can. We've done this. We put an Ethernet MAC, we put a PCI Express controller under that bump array. And some cases, it's not so convenient to do it that way, depending on how many thick metal routing layers you have on your silicon process. The easiest solution is if you get the micro bump array small enough that you can match your AIB IO array, like in the lower drawing here. It's just a very straightforward way to save area and without having to get super clever about using that other silicon area.
So you talked about in the interface area having the flip-flops. I assume that's for built-in self-test, scan test. Is that correct?
Well, the flip-flops are part of the, you know, how you sample the signal coming in. It's a clock-forwarded interface, a lot like DDR. So you get a bus of data and a clock, and you have to capture that data using that clock. So that's really what I meant with the flip-flops. But yes, they are scan-enabled because you do need it for IO testability.
Yeah, and I'm sure somebody will ask, so I'll ask. What about ESD protection? How's that handled? And I mean, is there some level of that in the interface, or?
Yes, yes. Yeah, in the AIB spec, we call out a 70 volt ESD requirement. We are, just for information, we're dropping that down to 35 volts on AIB 2.0, and it's really not a 1.0, 2.0 thing. It's really kind of the capability of the manufacturing equipment. And so that was kind of really the determining factor is, you know, these are not exposed to balls on a package. These are contained inside the multi-chip package, but still, you have to assemble these, and so some level of protection in Intel's assessment is still required. You know, ideally, we'd like to get to the point where you don't have to add any area for ESD protection, and so you could get your IO size down very small, because we have folks as part of the DARPA CHIPS program that wanted to, and we're working on 10 micron microbump pitches. And so now it puts a huge pressure on your IO design to fit within that 10 by 10 area.
Makes sense.
Great, thanks. Okay, so some more on the chiplet technologies for second generation protocols. So once you have the PHY under control, the next thing that occurs to any system developers, how am I actually going to communicate from one die to the other die? And after going through this, you know, over the years and looking at dozens of applications for this, we came to the conclusion that there were two drivers here, and as seen in the upper right here, it really depended on whether you were coming from the point of view of, I've got a PCI Express card and I want to collapse this all, integrate this all into a single package, and that's the package level integration. Or from the other direction, which is I have a monolithic design right now, and for reasons of heterogeneous integration, I want to disaggregate that. And so that was kind of a different use model. And protocols are really driven by the application, not the other way around. And so the protocol has to adapt to how the application is really trying to use the technology. And so we came up with these two categories here. So for the package level integration, these are commonly today PCI Express boards. They're things that are attached to a CPU. And there's a software model behind this that developers want a coherent memory model. So for distributed memory out there. An example of this would be the Compute Express Link, the CXL protocol. And from the other direction of people doing the SoC die disaggregation, you think back to Intel Stratix 10, where I showed you before, the previous generation ARIA 10 was a monolithic device, and then we split it up. Now, those are folks that are used to module-to-module interfaces. The ASIC developers like their lightweight protocols, things like AXI. A couple examples that are very relevant here are AXI streaming, AXI 4 memory map. So these are protocols that we're going to implement on top of AIB to really help that next level of chiplet developer. So just one page on each of those cases here. We're going to create an LPIF AIB PHY adapter. Now LPIF itself is a standard, and I've got the reference in the lower left for a common layer to put underneath CXL or PCI Express for that matter. And you can stack controllers on top of this. So you can imagine here's a stack on one chiplet. It talks down through the die-to-die PHY over to another chiplet, which has a similar stack. It's going to have an LPIF adapter and then the CXL or PCI Express controller above that. Now the die disaggregation protocols, these are folks, again, are used to it all being on die. And there are a couple of interesting cases here. The first one here, imagine you have some RF direct sampling ADC DAC. What you want to see is a stream of samples that are coming from your ADC, let's say, into the SoC. Typically, you're going to get a sample or group of samples per clock. So your transfer rate is linked to the sample rate. You're going to get data every clock. There, in this arrangement, is often no valid or ready required. It's just every clock you're getting a boatload of data, and you'd better be ready to take it. People are expecting low latency. There are some applications, electronic warfare, for example, that they want a very fast response. Be able to sample something and then go back and transmit something else based on what you received. And usually a very simple convention on how samples are packed. Now, off on the right side, we have a kind of a different use case. And this is exemplified by a memory controller on a chiplet. So imagine you had a GDDR6 memory controller on a chiplet and it's talking to its GDDR6 DRAM array. This is in the modern terminology, we call this a follower, not a slave, and we call it a follower, where the SoC is the leader and it wants to issue reads and writes. So it's going to do a cache line burst to read. It's going to send a block of data out on write. So you need a protocol here that's going to efficiently transport it, that's low latency. And unlike the other case here, the memory clock very well could be asynchronous to your transfer clock. And so AXI 4 is almost the industry default standard for memory controllers. So this is a really interesting protocol for this case. And so we want to build both of these protocols on top of AIB. Now the next area I want to talk about is how do we bring security concepts from SoCs down to chiplet scale? And if you just kind of think about it again, this is where, if you have a chiplet that could be 4x4, 4x8 in size, you can't afford a whole lot of space for it. So we have this target of less than a square millimeter that we want to spend on a security engine. This is a hardware root of trust engine where we would have public key encryption algorithms and AES cryptography in a chiplet framework. The security folks rightly start with the threat models of what are you trying to protect against. And a few of them I'll just describe here. One of them is these chiplets commonly have firmware in them. They have microcontrollers in them. The firmware gets loaded from somewhere else, FPGA, SoC, somewhere else on the system. It doesn't have its own attached flash or anything like that. This firmware can also contain proprietary algorithms for, let's say, ADC calibration, where you really would prefer that a competitor couldn't just easily snoop a bus and then pick off all your firmware and then go copy this or improve on it, leveraging your own IP. So you'd prefer that firmware comes across encrypted. So that's a mitigation to that threat model of firmware theft. Some other interesting ones are, what if somebody puts a malicious chiplet there? You want to know that it's an authentic chiplet that you are allowed to talk to, that you should talk to, so you can go authenticate that chiplet. So these are some of the threat models that could be addressed by chiplet security IP, and these are areas that we are developing for the SHIP program.
Is the AIB bus point-to-point, or is it a bus between multiple chiplets? And if it's a bus, could you put something else on the bus and not detect it?
It's a point-to-point quote bus. It's point-to-point. And the reason for that is, if you go to the electrical specs of this, the AIB interface is really a lossless, error-free interface. So we've calculated it, factoring the eye size, the various sources of noise, to be better than 10 to the minus 23 bit error rate. And we had a customer ask us about this. Well, why do you think that 10 to the minus 23 is good enough? And we compared it back to the device's native fit rate. And we demonstrated that this bit error rate on AIB was substantially less than the device's native fit rate. And so that was kind of an adequate response and proper response, really, to answer the question. So coming back to your question here, the way you get this kind of a bit error rate is through having a point-to-point bus. It's unterminated, it's very short, so you have a wide open eye where you can reliably, extremely reliably sample the data from one side to the other.
Yeah, and related to that, there was a question from the audience, is when you specified the bandwidth per millimeter, is that one direction or is that bidirectionally aggregated?
Yeah, this is a source of continual confusion, and I don't think there's any solution to it. I state this as Rx plus TX. It's probably the best way I can say. People say, well, is it full duplex bandwidth? You still don't know what full duplex means. So if you say Rx plus TX, you can kind of say, all right, you have this number of wires going this way, this number of wires going this way at that speed, and you add the two together, and that's the bandwidth per millimeter.
Okay, thank you.
Okay, so this is all great. We're able to get really high performance out of the advanced packaging of EMIB. The AIB bus itself, or these chiplets, could also be implemented on top of other technologies, RDL-based technologies, silicon interposer technologies, and there are people doing that. But there's another application that has really tough cost pressure. And you can think of a couple off just the top of your head. You think of IoT is going to be in this space. And some elements of commercial wireless are in the space also, of just crushing on the equipment suppliers and then down to their semiconductor suppliers of absolute lowest cost. And so this concept of having a high performance interface using standard packaging is a really interesting one. I think an inevitable one to serve this let's say mid-range. If I can just kind of create that, saying, if the optical network is way up at the high end, this is something less. It needs less than a terabit per second, Rx plus TX. And so if you can achieve that without using advanced packaging, you probably should. So a concept we have is, what if you just did an AIB that used a quarter of the number of bumps? And you can see my cartoon on the right here. Just says if you only use 1 out of 4, what could you achieve from that? And you compare it to the the full AIB 2.0 at 4 gigabits per second per wire, you get this 7 terabits per second. That's RX plus TX. You could achieve on standard packaging at 1/4 the density, a quarter of that, so close to 2 terabits per second. And part of what's going on here is through some clever package engineering, we think we can route this out on 3 layers, which if you go back to that comparison I had earlier on standard packaging technology versus advanced packaging technology, it was a 7 to 8x difference. If you could achieve this at 3 layers versus 2 layers on EMIB, you reduce that advantage down to 6x. So now it becomes within reach to do something interesting on standard packaging technology here. And so I think we're going to work on some development here because this is ultimately going to be a better trade-off for certain applications that don't need the maximum bandwidth. They do need significant, interesting bandwidth, but just have crushing cost pressure on them.
So actually a few questions here based upon what's being asked in the audience. Does the AIB standard define the maximum die-to-die spacing on the interposer and the package substrate?
It doesn't require a maximum. It gives you an eye diagram you must meet. And if you can meet that eye diagram, then it's up to you how far away you can space these. Now that's being very technical about it. The applications that we have, they're typically less than 10 millimeters apart from each other. And the cases that we have in front of us are less than 5 millimeters apart.
Yeah.
Kind of farthest ball from the farthest ball.
Mm-hmm. And your concept of here reducing, let's say, the width of the data bus to a quarter, does the AIB standard allow you to select the bit width of the bus to do this down select that you're thinking about with the bump placement?
Yes, so you could if you looked at the details of the spec, this is all within the bounds of the specification. We don't give a pinout yet for what would this look like with using C4 bump spacing. So when we're successful in this area here, I would undoubtedly have some addition to the specification that has bump diagrams, and there's some additional things since every single bump is precious here. You can't afford to use sideband per channel. So sideband signaling that would allow you to communicate extra status bits, calibration that we have, and we can afford on AIB 2.0 with micro bumps. You can't afford that with C4 bumps. So it's going to need some additional thinking about how do you achieve a calibration handshake from both sides. That yes, I'm up. Yes, I'm up. Now you can transmit data, reliably. So this is early work here. I know a number of people have been thinking about this, inside Intel and inside other areas for a year or so, but really developing this one here is going to accelerate over the next couple quarters.
Okay, thank you.
Great. So that's really, I'm at my wrap up here. The chiplet idea is very popular. It's super engaging, interesting to me personally. Chiplets are still a lot of work to build. You've got to build an ASIC, and our experience is you spend months in the back end when you're way past all your functionality just to get all your DRCs and ERCs complete and get this suitable for tape out. So at the front end of this, the standard is helping, IP is helping. AIB IP is available from a few different companies: Synopsys, Intrinsic Corporation out of Massachusetts, and Blue Cheetah out of San Francisco. The protocol and utility IP will reduce the effort here and really help interoperability, so that the people trying to do the same thing do it the same way. So Ira asked me at the start here, really, what's my call to action? And I would say it's this middle one, perhaps for this group here, which is, the cost of advanced packaging is driving alternatives. Clearly it has a space here. We use this extensively inside Intel, and there are applications such as the ones I mentioned with optical networking and direct RF sampling that there is no alternative to advanced packaging, high density technology. But there are cases where the cost of it, if you can solve it some other way, it's driving some alternative choices, and really for gigantic applications, really multi-billion-dollar cases. You can just think of the Intel CPU as one of those. You can do whatever you want. The NRE doesn't matter quite as much because your recurring cost is much more important. But in other cases, such as military applications, the cost of NRE is very substantial amount of your total project cost. So the call to action I'd have for this group is, what can you do to increase the availability of advanced packaging? So Intel with the Ship Factory is doing a big step there. What can you do to reduce the cost of advanced packaging? Can you make it where it's cents more rather than dollars more to do this? That would be something really helpful and would really accelerate the adoption of advanced packaging. The last point I have is Intel and the U.S. government's making substantial investment in chiplet design technologies. This gives us muscle to continue our chiplet leadership, and to another one of Ira's points, much of this work we're going to put out on GitHub as open source. Helps us, helps our competitors, helps our customers, and I think this is just for the good of the ecosystem, and ultimately it is good for Intel to do this because we will have a stronger base of customers. So with that, Ira, I'll take any questions, any more questions if there are any.
Oh, there are lots of questions. So
Great.
let's see if I can group these in some order that makes sense. So I think there's a lot of questions about the actual interconnect of the AIB interface. I think you've basically answered this one, but somebody asked, we're using thin film technologies that can meet AIB 1.0 specs for DoD applications. These are very economical. We heard that Intel was researching this as well as alternative to EMIB. Is this true? I mean, obviously you have your EMIB technology. Do you want to make any comments about other ways you're thinking of implementing things?
Maybe I can answer sideways or half answer this.
Okay.
Look, my experience working with the Intel's Advanced Technology Development Group is I'm extremely impressed. There's probably no packaging technology that people are not researching in one form or another, and it's ultimately what gets taken to production is what has the business imperative and the capability to take a new technology into development. So you think something like Intel Xeon. If Intel Xeon needs it, absolutely will go to production.
Yeah, yep. And related to this, there was a question, high data rate at fine pitch needs ground shielding. That means your layer count will go up, shifting more burden on the C2C, the chip-to-chip integration platform. On the contrary, wider beachfront leads to area increase. Have you thought about where the crossover point is, or?
All those statements are true, and we try to find a minimization between the two as far as recurring cost or silicon area or bridge area goes, because we use combination of different means of shielding, perhaps is the right way to say it, and yes, you've got to use both microstrip and strip lines. And we use guard traces and planes. It's probably not any one direction or the other. When people are faced with extreme cost pressure, they will do whatever it takes to come up with a solution on this. But what we have been able to do very successfully is once we've designed a solution, we've been able to reuse the Stratix 10 EMIB, that's the bridge, for all those chiplets I said are already powered up. I'll use the same Stratix 10 bridge. So it's kind of once you solve that problem and then you give the model here to the chiplet developer, they can simulate their chiplet up against that model here and ensure that they meet the adequate eye diagram.
So just to clarify, you've only basically produced one version of the Stratix 10 EMIB and you've used it on multiple projects.
Well, we've produced more for Agilex and we'll produce more in the future. But what I'm saying is it's very reusable. That once you get that point, you can imagine with AIB 2.0, we're going to develop a new EMIB here because of the higher data rate and the new set of simulations that have to be done in order to prove that low bit error rate signaling.
Okay, got it. Let's stay in the and actually one more question, and this is more EMIB related. Is EMIB only die to die, or could you connect more than one chip to 2 or 3 other chips with an EMIB?
Okay, I'm just kind of visualizing something here of, could you have something that looks like 2 chips on the left side, 1 chip on the right side, and can you connect them all 3 together with EMIB? This is where I'd go to someone like Ravi Mahajan and say, hey, can we actually build this case? There have been a number of these, and typically the technology is very capable, but a specific answer to that one, I'd have to see the exact case.
Okay, got it. Okay, wow, they're still coming in like crazy. Let's go in a different direction. Chiplets in general, do they help address the thermal management problems that these large die are having? And
we're still in the realm of 2.5D here. My gut feel is that it's probably a wash. I mean, you think about it, if you just kind of look top down at it, and let's see if I can reach one over here. From the top down, it kind of looks like your die just got bigger here.
Do you want to, why don't you stop your video share and then you'll go full screen? That is the way people can see that a little better.
Oh, the desktop. Okay.
Yeah, just stop your screen share, or I can do it.
Okay.
No, hold on. Here, there you go. Now you're full screen.
Okay.
So
anyway, it's going to just show this one. This is a test package we did here, and you just think on the surface area here of the FPGA main die over here to this E tile here on this side here. There's a 100 micron gap between those 2 die, so when just kind of top down on it, you still have the same surface area you're working with. So in that sense, it's mostly a wash. Interestingly enough, if you have a hot spot on the chiplet, it might be an issue that you don't get to diffuse it across the large monolithic area here. But we've had to, for a long time now, do a hotspot analysis on the thermal solution. So I would say it probably doesn't create any unique challenge in that respect. You still have to do analysis and a solution for it.
And in terms of packaging, so obviously these are going to drive your actual, let's say, package substrate, laminate, whatever. And one question was, once you get to large packages, I mean, maybe the part you have is somewhere in the 70 to 70 millimeter, or maybe as large as 120 square. Are there going to be CTE issues between the package and the PCB? are we going to have to go to new type of interconnect technology there? If this is an area you feel comfortable commenting on.
Yeah, it's, you know, in the domain we're talking about, such as something like this, you know, it's a
Right.
55 by 55 millimeter package. There are other areas inside Intel that are really pushing the larger package sizes. Some areas like photonics, network switches that are doing, you know, larger than this. So they're probably breaking the ground on the thermal expansion differences between the package and the PCB. And we kind of get to ride on the developments that they're making there. The between the chiplet and the substrate, the challenges there have not been substantial so far for the scale of packages that we're talking about here. You know, of things that are in this range, maybe goes up to 65 millimeter size package. You know, we've done a multi-main die FPGA. Xilinx has done multi-main die FPGAs for a long time in that area.
Okay, great. Okay, so let's move on. We talked about thermal. Let's talk about, well, actually, related to thermal, I mean, how much power is dissipated by the AIB interface?
Okay, so that's when the picojoules per bit helps. So one terabit at 1 picojoule equals 1 watt. So you can see that 7 terabits at half a picojoule would be 3.5 watts for the interface. So that's kind of why the you know, so it's a kind of an easy rule of thumb to scale it appropriate there, but it absolutely puts pressure on reducing the energy per bit for sending data across, because it is more than on die, but it's a lot less than previous generation SerDes technology. I think some short reach SerDes start getting, you know, into the single digits picojoule per bit, but at the same time the parallel technologies are advancing as well. And so that's why things like you know, people get interested in ESD, is how much of a capacitive load do you have there. We're scaling the voltage down to reduce that power dissipation.
Okay. Okay. And in terms of, you know, chiplets, if you've got lots of little chiplets and each need a bridge, well, you can either go to, let's say, a monolithic silicon substrate, but if you're looking at the bridge approach, is there a technical or practical limit to the number of bridges that you could put in a package, or, you know, or where's the state of the art on that frontier? Or
I think it would ultimately come down to a yield equation is probably where it's going to go. You know, we've seen excellent yield on our devices. We implement redundancy so that you can have an open bit and then route around it. You know, a lot of things that's been done on HBM as well. So I think a combination of those techniques help with improving yield. There have been people who proposed some remarkable number of chiplet concepts. You know, we've got in production, you know, ones with 6 chiplets right now. So I think, you know, anywhere in that single digit range is easily within reach.
okay, got it. Let's talk about the ecosystem. Do you think that the chiplet market, a marketplace, will evolve, or will be individual companies like those selling IP today? You're going to be able to look up a catalog of chiplets, or, you know, through like a physical distribution company, or is it more you got to go sign your partnerships with each entity and everybody co-design?
Well, I think it's my thinking on this is it's likely to be a lot like the analog digital converter market right now. that you end up with some market leaders, people like Analog Devices, Texas Instruments, and that they will offer these chiplets. And I think that's kind of why there's so much an interest on standardization, is that they can have one item instead of n items that they need to support there. But I think that's the kind of marketplace we're going to see is more towards the folks who have IP that you can't just easily stick in your own digital design are the ones that are going to offer these.
Yeah. And is there, you obviously you talked about the AIB spec, but how do the physical data of the chiplets be, communicated? The thermal, the physical size, the chip design. Has there been any standardization there, or is it still, are we back to Excel spreadsheets and CSVs?
I kind of think that is there's going to need to be a data sheet. So you can extrapolate a lot from, what a discrete devices on a board do right now. You can extrapolate a lot from that. You need to understand the data sheet. You need to have models for how to talk to it. You need to have thermal models. So I think going from that kind of methodology is very straightforward. I know there's some efforts in OCP. One of your previous speakers might have talked about that, of having a database of chiplet capabilities. That sounds interesting, and if that can be developed, that would be helpful.
Okay, yeah, and this is I think related to the market and relating to EMIB. Is this a technology that Intel is going to license to other people, to the competition, or is that going to be Intel specific offering? If you know the answer and can answer it. So, I mean, what should people expect?
Well, I can tell you the way it is, and that the EMIB is proprietary to Intel. That we have not licensed it to other people to build it, and that was a strategic decision for Intel. The chiplet idea here is not tied to EMIB. As I mentioned, there are people looking at how to do this on a silicon interposer, how to do this using an RDL technology. So I expect that that's probably how this is going to continue. Is that its accessibility to that technology is something that I think would help the ecosystem. With Intel building the chip factory, if other players could make their technology more available to anybody with less than $50 million or so, if you're a huge account, you get whatever you want, and the real question is, somebody who's not a huge account, how do they get access to it?
Right. And it's the challenge of the marketplace and the market incentives. So we have more questions. I don't know if you want a few more, or
sure, I can take a few more.
Okay. And this relates to well, this one relates to at the high level and outside this U.S. government engagement. Can you talk a little bit more about the Intel model for this business, for chiplets and packaging for outside entities? I mean, how do people either qualify or engage? Is it somebody's got to come with a blockbuster design, or could a startup come up but just knock on the door of somebody at Intel and say, how do we get going with this?
Okay, so the chip factory is intended to help that substantially, to get to a model where for a reasonable cost, an IP developer who has a chiplet says, hey, look, Intel, would you assemble my chiplet? Maybe I want to hook it up to one of the FPGAs. Maybe I have a different ASIC. It doesn't have to be an Intel FPGA. It doesn't have to be Intel Silicon. That model will run through the chip factory. There's the existing model we have, which is we take it and we make it an Intel product. So that's another path forward. and that one's going to be more, does this match up with Intel's product portfolio? So the first one I described is probably more to what the questioner's thinking of, is how would somebody else engage to get their product assembled using this Intel's advanced packaging technology, and that's what we're developing with the SHIP factory.
And to be clear, the SHIP factory is more than just the AIB spec. I mean, the SHIP factory is driving that ecosystem and players forward, or what is the ultimate deliverable of the DARPA project? Or there's probably more than one.
Okay, so let me back up a little bit. So the U.S. Navy awarded Intel the contract for SHIP to build a factory for providing access to the Defense Industrial Base to use Intel's packaging technologies. So idea is these folks would come in with their own silicon, with third-party silicon, and say, Intel, please assemble this for us, or help us design a package to put these pieces of silicon together. So that's the bulk of the SHIP contract. And in addition, as I mentioned, it's the U.S. government was interested in advancing the chiplet technologies in the areas of interfaces, protocols, and security.
Yeah. Okay. So, for example, one of these, shall I say, black dies out of Fort Meade could be shipped to you guys, and you would integrate it for the spec into a package and deliver it at some point in the future.
Okay. At this point here, we don't handle export controlled material.
Right.
That's today.
You got it. Okay. Good. I think we can connect the dots. Okay, that's fine. Okay. Okay. And will there be any new, from your perspective, any new requirements for testing these chiplets that, obviously looking at 36 micron pitch micro bumps is a huge test challenge for physical contact, but your work on AIB and chiplets, do you see additional challenges that the test industry is going to need to solve to make sure you can get yields where they need to be?
There's the question everybody has about known good die. How do you produce known good die? And are you able to probe micro bumps? That's a big challenge right now. A lot of what we do involves non-contact technologies. Absolutely, I think as this thing advances, Intel announced at Architecture Day a technology called ODI, which goes even smaller than what I showed as far as micro bump technologies. So there's going to be continual pressure on how do you test those. So I guess I would agree with the questioner, and I don't have the answer or the solution right now.
Okay. Okay. So one last, hopefully simple question here. 10 to the minus 23 bit error rate. Has that been validated in the silicon, or is it a statistical projection? Given such a good BER number, what error detection or correction schemes are recommended, or do you even need one in the protocol?
Okay, it is not possible to validate in silicon that bit error rate, even out of having 6 AIB full AIB interfaces. It just takes too long. I think you can calculate it out. It's in the last time I did it, it's dozens or hundreds of years to see an error. So you can't practically validate that. It's done through analysis, and it's not just as simple as looking at electrical specs. You do have to factor in noise profiles, and that's how we've calculated the bit error rate. Now, the trivial level of validation is we put this on the bench and we don't see any errors, so it doesn't validate it, but it just tells you we're not completely on the wrong track. Now, given this, we have not needed to implement any error correction, and that it's because of that very high standard. So you could run the link much, much faster get a much smaller window, and then start dropping your bit error rate, but then you would have to implement error correction. So there's a lot of discussion about that. You know, is ECC adequate? Well, it probably is. Do you need to have a retransmission protocol? Well, okay, that would solve it. You know, that works for PCI Express, but then you lose this kind of monolithic type design of you know, single digit nanosecond latency if you have to start doing things like retransmission, which would put a huge bubble in your data traffic. And it's really impractical for some of those applications I was talking about. So we're committed to keeping with a very low bit error rate so that you don't have to implement error correction or error detection retransmission.
Great. Okay. So Dave, there are even more questions, but I think we're just going to have to call it at that point. I thank you very, very much. Let me do our closing here. So reminder, December 9th will be Sandeep Razdan from Cisco. That will be a live only event. And December 16th will be our holiday hangout. So please join us for those. And if you're interested in presenting at a future webinar in the new year, please contact myself or Dave Town. And please save the date for February 9th and 10th for the Too Hot to Test event. And we're looking for abstract proposals by December 18th of this year for the program for Too Hot to Test. And with that, I will wish everybody a good rest of your day. Thank you again, Dave. And we look forward to seeing everybody at a future semiconductor industry speaker series. Thank you.